Good afternoon, everyone. I'm Nan.
My name is Sergey.
Today, we'd like to give you a lecture about the dynamics and control on traffic jams. We're doing this research this summer under the supervision of Professor Gabor Auras, affiliated to Department of Michigan Mechanical Engineering.
So we're doing this research because in the past couple of decades, autonomous cruise control systems have become more common in vehicles. So in these systems, we have sensors on vehicles that sense not only the speed of the vehicle that has this system, but also the speed as well as the distance in between the vehicle in front of this vehicle that has this system. So because such systems are becoming more common, it's necessary to analyze if they are safe, to analyze if the system is stable, can it go unstable, and are there ways of improving the system. In this paper, we would walk through the development of the two traffic models that use to analyze this system. We'd also analyze the characteristics of these models. And then we look at ways of modifying these models so that we can improve on some of the characteristics of them. We then will try to develop a sort of a framework that would help us to analyze these systems in a more rigorous manner, which will probably help us to get some more specific conclusions about this system.
All right. First of all, I would like to introduce the Platoon model for journal model for two cars following. The two cars are running in a continuous time and continuous space. The leader is denoted here as n+1 and the follower is n. The distance between these two cars are denoted as hn. Two cars, we have a dynamic model, so the acceleration for the follower is a function of hn, vn, and hn dot. We add another parameter, which is the acceleration of the leader, denoted here as vn+1 dot. And to make the expression simpler, we apply the parameter f, g, h, and j as the partial derivative value for the equilibrium state. And to linearize this model, we get this. And also, we use the Laplace transform method to get the transfer function, and we would like to analyze the stability issue to this system and the plane stable. To get a plane stable, we need the characteristic roots for the denominator of the transfer function to be negative. Given that g and h is bigger than 0, we can get the plane stable for f to be greater than 0. And we define the string stability as the behavior, like the speed of the leader will decay in the follower's behavior. So we wanted to know that what the f value we pick could keep the string stable. We substitute s by j omega and take the absolute value of that, let it smaller than 1. We notice that if j is greater than 1, then f should be negative to get a string stable, which is conflict with this plane stable. F is greater than 0, so we constrain j to be less than 1, and we get this inequality. It is clearly shown in this equality that 5 parameters that can influence the stability, which is g, h, j, f, and omega. As g and h increase, the range for stable region for f is increasing. As same conclusion can be applied to omega, but j, the influence of j to the region of f is kind of complex, so we plot a stability graph for f as a function of j given a fixed g and h. You will see in this graph, as omega approaches to 0, the stable region is decreasing, and the region with blue crossed line is a region that is string and plane stable whenever the omega is. You can see that for every critical f, it always crosses the point of -1 and 2g plus h times h divided by 4. which is clearly shown in the equality above, which we insert j equals to -1, we get this value. And we have another issue which is called the overshoot, which is defined as the output signal exceeds the input signal. In our case, that is, the follower speed will be higher, will exceed the leader's speed if the leader is in a constant speed. We don't like that issue. We will discuss this more in the following slides. We also plot the region which is the black cross line where there's no overshoot. To validate this plot, we pick 3 different points, which is 1, 2, and 3, and use MATLAB ODE 45 to simulate. You can see in graph 1, we pick the point with f and g within the region with no overshoot and plain and string stable. You can see in this graph that if leader is in step input, the follower speed never exceeds the leader speed, and when the leader is in frequency input, the follower's amplitude, the velocity of the follower's amplitude, is also smaller than the leader. As to the second point, you can see that for the leader, the amplitude for the frequency is also greater than the follower. However, when the leader is in step input, which is with a constant velocity, the velocity of the follower tends to exceed the leader, which may cause a dangerous thing. We don't like that. And the third one is pretty dangerous. You see, it not only has an overshoot, but also string unstable. Things we talked just now are for general model. To get a further analysis, we need to assign a specific expression for our model. So we pick the optimal velocity model, which is a classical one. In this expression, the first term of the right-hand side of the equation represents a relaxation of a driver tends to drive in a speed with v as a function of vh, and as we discussed before, we can calculate the parameter f, g, and h accordingly. First of all, I'd like to apply this model to a piecewise linear VH. In this function, the driver tends to stop when the interval distance between the leader and follower is smaller than h stop, and the follower will tend to go on maximum speed when the interval distance is greater than h go. In between, the driver tends to keep the time distance a constant. And this is there's a problem with this model, because near the h stop and h go, there will be sudden changes for the equilibrium velocity. To avoid this, we simply apply a smooth curve sinusoidal function to eliminate this. We also would like to analyze the stability issue for the piecewise linear. We can get from the previous inequality with j equal to 0, then the string stability for f is this formula, and apply the value we just calculated, we can get such t gap, beta, t, and omega. Notice in the piecewise linear model, the stability do not have a relationship with h star between h stop and h go. You can see in this graph, as omega decrease approaches to 0, the region for stability is decreased. So in order to get the stable state whenever the omega is, we better choose the region on the right bottom side. And for the smooth curve, it's not that simple, there's a relationship between the parameter h also has an influence on that stable issue. We can solve the equation and get the answer to instability and plot the stability plot as a function of h and the t inverse. In this graph, we're given a t gap equal to 0.5 and also equal to 0.5, and the bell shape, inside the bell shape, their state is unstable and outside are stable. Then we fixed t gap to be 0.5 varies the frequency omega. You can see in this graph as omega increasing, the stable region also increase. And this time we fixed the frequency omega to be the same and vary the t gap. You can see the stable region is deformed. As to the multi-class simulation, we'd like to show you how serious the overshoot issue is. We apply a piecewise linear model for multi-cars and pick 6 cars as an example. First of all, we set the step input for the leader to be 15. The linear model tells us the equilibrium is at h equal to 12.5 and v equal to 15. Set initial for every car to be this value, and you will see that for every following car, the maximum velocity is increasing. If the number of cars increase, you can see the velocity will even increase more. That will probably cause collision. This is, for the frequency input, that's also the case.
Thank you, Nan. And another way to approach this problem is to take a look at the circular traffic model. In this model, unlike the Platoon model, we have n vehicles which move around a circular track, one after each other. This track is of a given length, and then each vehicle's acceleration is influenced by the speed of the vehicle, also by the distance between the preceding vehicle and this vehicle, and by the change in this distance or the relative velocity of the vehicles. So we have chosen that the acceleration would be a function that is actually exactly the same as the function Nan had used to model the acceleration of the vehicle depending on the positions of the vehicle in front, as well as the changes in relative velocity and the speed of the vehicle. So the first thing to do for this model is to linearize the system around an equilibrium. For this system, the equilibrium would be when the cars are traveling at the same speed, as well as the cars have an equal distance in between each other. So when linearizing the system, we obtain terms for the first order derivatives, which are also similar to what Nan has shown in his analysis. After this, we want to take a look at the characteristic polynomial for n vehicles. So from this polynomial, we are able to obtain the eigenvalues, 2 of which would be real eigenvalues, and the rest would be complex eigenvalues. So the results show that in this case, the only kind of bifurcation that is possible would be a supercritical Hopf bifurcation. In such a bifurcation, if we keep f below a certain value, which is given by equation for the critical f on the left side right now of the screen, the velocities would actually tend toward an equilibrium, so the system is stable. As we increase this parameter f a bit more, we're going to have a limit cycle forming, which means that although the origin will still be slightly stable, the cars would tend to oscillate. And if we increase the parameter f even more to supercritical values, you're going to get the origin becoming unstable. By the origin, I mean the equilibrium. And the limit cycle will become larger, and this would be the cycle to which the cars tend to oscillate around. So we also, in this study, take the limit of n as n becomes very large. This is very important because large n's represent a single lane road when we put in more and more vehicles into this circular traffic model. So in this case, f should be also less than the certain value on the screen to become stable. Now, after analyzing this stability, we have chosen to modify this system to see if this modification could improve our system. We introduced a new variable j. This j would be a unitless constant, which would represent a sensor that would sense the preceding vehicle's acceleration and then scale it to the acceleration of the vehicle that hosts the system. So for such a model, we have a new equation that describes the acceleration and a new characteristic polynomial with an extra js squared term on the right. In the results, we still get a Hopf bifurcation of the system, and we get another new parameter that would be, again, if the system is below this if the system has a parameter f below this parameter, then our system is stable. But as we get at this parameter and above this critical parameter, then the system becomes unstable. So in the limit that n becomes large, this value is actually very similar to the value that we obtained earlier, and is also very similar to the result that Nan obtained for his stability analysis. The only difference is that we get this 1 minus j factor on the bottom. So this factor actually turns out very important when you look at the stability plots for the critical f versus j. Because of this extra parameter j, we get that that the real eigenvalue of this system would actually be going through another bifurcation in which it will change from a stable eigenvalue to an unstable eigenvalue at j equals 1. Because for this specific system, the value of this eigenvalue is negative h over 1 minus j. So there's going to be a very dramatic change from the system being stable to a system being unstable when we cross this boundary. So in this case, we cannot use any j that's greater than 1 because it will dramatically destabilize our system. However, we can take a look at parameters less than j equals 1. So for parameters less than j equals 0, we can show from taking the partial derivative of the expression for f in terms of j below that every single value of f critical would be actually lower than the value for f critical at j equals 0. So we don't want to use j's that are less than 0 in this case. However, we can use values in between 0 and 1 for j, and that will actually improve our stability. It could be a drastic improvement, but once again, we do not want to get close to the j equals to 1 boundary because that will destabilize our system through a different eigenvalue. Also, we have taken a look at the different numbers of vehicles. So for different numbers of vehicles, we get that the right branch of our stability chart gets flipped around as n tends to infinity. However, this change does not really matter because we do not want to consider j's that are greater than 1. Lastly, we wanted to establish some sort of a framework in which we can work with this system in the future, and maybe this will allow us much simpler analysis of the system. So we can do that by diagonalizing our system. We do that by considering the matrices called the Laplacian or the adjacency matrices, which actually share the same sort of couplings that our Jacobian matrices have. So by transforming these matrices and obtaining the resultant transformed Jacobian, we get that it's in fact a block diagonalized system with a for the 3-car model, it's going to look like the one on the screen below. So each of the blocks A, B, and C are actually 2x2 matrices. These matrices actually give the equations for the specific modes of the oscillations that occur in our system. So A and B and C would each be a separate mode that you would consider. So this form is also important because now we have 3 decoupled second-order complex differential equations as opposed to one that's 6th order. So it's actually would be much quicker to analyze. And in fact, this transformation we can do as well as for the original system, as well as for the one with the parameter j, because it can be proven rigorously that Jacobian with the j can also be diagonalized by using the adjacency in the Laplacian matrices. So for the conclusions, including the acceleration of the leader, which how we modified our system, is actually beneficial if you keep the j within a certain value, but must be taken care of, because if we play around with the j too much, we can actually destabilize the system. And
for the linear analysis, they gave us some indication of what happens at non-linear level, but rigorous analysis is required to characterize the non-linear behavior.
Of course, we have answered several questions about the Platoon and the circular track model. However, it would be desirable to look a bit more thoroughly to provide more rigorous analysis of this system. So there are quite a few directions in which we can go from this introductory study. We can, of course, make a more thorough analysis of the Hopf bifurcation to the 3rd order, because that will give us more specific information of what happens there. And we can also examine rewiring the ACC sensors so that we not only sense the vehicles that are in front of us, but also, for instance, sense the vehicle that's 2 vehicles in front of us or 3 vehicles in front of us.
And also we can develop in analyzing more realistic traffic configuration, for example, for the city networks. That's the end of our lecture. Thank you very much.
Thank you very much.